We have a large number of cars. We have millions of cars that will be able to operate autonomously by adding their car to the fleet for autonomous use.
Tesla and SpaceX have developed a new motor technology that could obliterate all other electric vehicles. And no, we're not talking about a 10 or 15% improvement over existing technology. We're talking about efficiency gains of up to 40%. The kind of breakthrough that comes along once in a generation. And if the results are true, then cars could travel hundreds of miles farther using the same battery. Manufacturers could build cheaper vehicles. And entire industries built around lithium, cobalt, and battery production could suddenly find themselves facing a very different future. So what is this new revolutionary technology? And how did Tesla invent this? To understand this, let's take a closer look at how EVs started in the first place. The birth of EVs. In 2025, 1 out of every 4 cars sold was an electric vehicle. Total global EV sales reached 20.7 million units, a 20% jump from the year before. An industry that sold only a few million vehicles annually in the mid-2000s had quietly become one of the biggest growth stories in modern manufacturing. But it all started way back in 1996. That year, General Motors, the largest car company in America, quietly leased a small fleet of electric vehicles called the EV1 to customers in California. The cars were fast, smooth, and completely silent. People who drove them loved them. Some loved them so much they tried to buy them outright rather than return them at the end of the lease. GM refused. And then, in one of the most controversial decisions in automotive history, the company recalled every single EV1 it had ever built and crushed them. Owners showed up with checks in hand, hoping to keep their cars. The answer was still no. For years, the electric car dream seemed dead. But then a new technology changed everything. In the early 2000s, engineers realized that lithium-ion batteries, the same batteries powering laptops and mobile phones, could finally make electric cars practical. They stored more energy, could be recharged thousands of times, and kept getting cheaper every year. That breakthrough opened the door for a small startup founded in 2003 called Tesla. After years of trial and error, Tesla launched the Roadster in 2008, proving that an electric car didn't have to be slow, boring, or unattractive. But the real game changer came in 2012, when Tesla introduced the Model S. For the first time, an electric car offered enough range and performance to compete directly with traditional gasoline vehicles. And suddenly, the fear of running out of battery before reaching your destination didn't seem like such a big problem anymore. The rest of the industry noticed. By 2020, almost every major automaker had announced plans to go electric. Volkswagen, Ford, General Motors, Toyota, Mercedes-Benz. The race had officially begun, but there was a huge problem. The problem with EVs. In 2010, most electric cars could barely travel 100 miles on a charge. By the mid-2020s, many popular models could comfortably exceed 300 miles, while premium vehicles pushed past 400 miles. At the same time, battery prices also collapsed from around $1,200 per kilowatt-hour in 2010 to below $100 per kilowatt-hour in some cases by 2025. It looked like the industry had cracked the code. But beneath the headlines, a different reality was emerging. The lithium-ion battery, the technology powering nearly every modern EV, was beginning to run into its natural limits. You see, the one way engineers improved these batteries was by increasing the energy density. Essentially, how much energy a battery can store for every kilogram of weight. The gains were impressive at first, but by the early 2020s, progress had started to slow. And the reason was simple. Lithium-ion batteries are based on chemical reactions, and every chemistry has a theoretical limit. Engineers cannot squeeze unlimited amounts of energy into those chemical bonds, no matter how advanced the technology becomes. But batteries weren't the only issue. Charging speed was becoming a problem of its own. Automakers have been spending millions developing ultra-fast charging systems capable of adding hundreds of miles of range in less than 20 minutes. But there is a trade-off. When you force large amounts of electricity into a battery in a very short period of time, the battery generates heat, lots of it. Heat is the enemy of battery health. Over time, repeated exposure to high temperatures gradually damages the battery's internal chemistry. The process is slow and often invisible, but it adds up. A battery that delivered 300 miles of range when new might provide 270 miles after several years, then 240 miles later on. Most drivers don't notice until they suddenly need that missing range. Then there was another issue that received far less attention: where the materials actually came from. Every lithium-ion battery requires huge quantities of raw materials. Lithium, nickel, cobalt, manganese, graphite, and rare earth elements all play critical roles in modern EVs. The problem is that these resources are not evenly distributed around the world. More than 70% of global cobalt production comes from the Democratic Republic of Congo, while China controls the majority of the world's battery processing and refining capacity. In other words, the EV revolution was reducing dependence on oil-producing nations, but it was creating dependence on a different set of supply chains. Any global supply chain disruption could have a ripple effect throughout the entire industry. By the middle of the last decade, it was becoming increasingly clear that simply improving lithium-ion batteries might not be enough. The battery wars between 2018 and 2024, a global race began. On one side was the technology that had been called the next big breakthrough for years: solid-state batteries. See, the thing is, traditional lithium-ion batteries use a liquid electrolyte to move energy between electrodes. Solid-state batteries replace that liquid with a solid material. In theory, that change solves several problems at once. The batteries can store more energy in the same space, potentially increasing vehicle range by 30% to 50%. At the same time, they can charge faster. And because there is no flammable liquid inside the cell, the risk of battery fires is dramatically reduced. It sounded like the perfect solution for every EV problem. So, the world's biggest companies took notice. Toyota invested heavily in solid-state research. Samsung expanded development programs. Startups raised billions of dollars to back the next battery revolution. Every few years, a new announcement appeared claiming commercial solid-state batteries were just around the corner. But the problem was that the timeline never seemed to get closer. Back in 2019, many battery researchers believed solid-state technology was roughly 5 to 7 years from large-scale production. By 2024, experts were still giving almost the same estimate. The technology works in laboratories, but mass-producing it at scale remains a completely different challenge. So, while most researchers chased the battery of the future, another group took a different approach. Instead of reinventing the battery, they focused on improving the one that already existed. Companies spent billions refining conventional lithium-ion technology. The goal wasn't a revolutionary leap, it was thousands of small improvements added together. No company represented this strategy more visibly than Tesla. In 2020, the company unveiled its 4680 battery cell, named after its dimensions, 46 millimeters wide and 80 millimeters tall. The cell was larger, simpler, and designed to be cheaper to manufacture. Tesla claimed it could improve vehicle range while reducing production costs at the same time. By late 2024, Tesla had produced its 100 millionth 4680 cell, marking one of the greatest battery manufacturing efforts in the company's history. But while Tesla was busy developing its new lithium batteries, another battle was taking place thousands of miles away. China was quietly becoming the center of the global battery industry. Their battery packs had fallen from costing more than $1,100 per kilowatt-hour in 2010 to some manufacturers reporting prices as low as $130 per kilowatt-hour. Tesla's new technology. At the 2024 Tesla event, details began quietly emerging from Tesla's engineering teams about an electric motor technology that had been developing behind the scenes for years. During the event, most people were focused on Tesla's 4680 battery cells, expanding production in Texas, and improvements in charging speeds, cooling systems, and manufacturing efficiency. But buried within technical presentations, research papers, and live streams watched by only a handful of specialists, another story was beginning to emerge. This wasn't about making lithium-ion batteries slightly better. It was about replacing parts of them altogether. And do you know where the breakthrough came from? SpaceX's Raptor engine program. Now, I know what you're thinking. What does a rocket engine have to do with an electric car? It sounds completely unrelated, but stay with me. This is one of those connections that most people missed. At Tesla and SpaceX, engineers don't work in isolated worlds. People move between teams. Ideas move with them. A solution discovered in one field can end up solving a problem in another. And that's exactly what happened here. To understand this, we first need to look at what made the Raptor engine such a big deal. The Raptor uses something called a full-flow staged combustion cycle. It is one of the most efficient rocket engine architectures ever attempted. Because for decades, engineers thought it was theoretically possible. But creating something like this was going to be extremely challenging. The Soviet Union experimented with similar ideas during the 1960s in the RD-270 program, but the technology never became operational. For more than 50 years, nobody successfully built a reusable full-flow staged combustion engine that worked reliably at scale. Then SpaceX decided to take a shot at it, and they didn't follow the traditional aerospace playbook. Instead of spending years perfecting a design before testing it, they built hardware fast and tested it even faster. Some engines failed spectacularly. Others exploded during development. But every failure produced data, and SpaceX kept iterating faster than traditional aerospace companies typically could. By the time Raptor 3 appeared, the engine was reportedly generating around 280 metric tons of thrust with a vacuum-specific impulse above 350 seconds. To put that into perspective, those numbers would have sounded almost unrealistic to many engineers just a decade earlier. Now, obviously, Tesla wasn't looking at Raptor and thinking, let's put a rocket engine in a car. That would be ridiculous. But they were looking at the technology behind it. What if the same mindset could be applied to electric vehicles? What if, instead of endlessly optimizing existing battery and propulsion systems, you redesigned the entire energy cycle from the beginning? Redesigning the system. But before we get into how this technology works, you first need to understand where energy is actually being lost in a modern electric vehicle. Most people imagine that electricity leaves the battery, goes into the motor, and turns the wheels. But the reality is much messier. Every time energy moves through the system, a small portion of it is lost. Some of it is lost in the inverter, which converts the battery's direct current into the alternating current the motor needs. A portion is dissipated through electrical resistance, while some is converted into vibrations and heat. Now, it doesn't seem huge, but all these losses add up. by the time the energy finally reaches the wheels, a meaningful portion of what came out of the battery has already disappeared. And for decades, engineers have dealt with this problem in basically the same way. They have accepted that these losses are unavoidable and focused on managing them as efficiently as possible. And to their credit, they've done an impressive job. Modern electric vehicles are already incredibly efficient. However, this new architecture from Tesla takes a completely different approach. Instead of asking, how do we deal with the energy that gets wasted? It reshapes the entire thinking process. How do we prevent that waste from happening in the first place? That is the same philosophical shift that made staged combustion rocket engines so revolutionary. This new motor architecture applies the same idea to electric vehicles. Rather than accepting losses at every stage and dealing with them afterward, this architecture appears to attack the problem at its source. The result is a motor that can produce more mechanical output from the same amount of electrical input, and it does so by maintaining the peak efficiency of each component. Industry reaction. When the early efficiency data from this new motor architecture began circulating through engineering circles, the reaction from the wider automotive industry was surprisingly quiet. There were no public statements from the battery research divisions at major OEMs. There was, mostly, silence. And in highly competitive industries, silence can be revealing. Because if the reported efficiency gains are real, the implications extend far beyond the motor itself. A motor architecture that converts 30 to 40% more of the battery's energy into motion means a vehicle that needs 30 to 40% less battery to travel the same distance. And since the battery is often the single most expensive component in an electric vehicle, that has the potential to dramatically reduce costs. But the implications go far beyond price alone. Today, a typical long-range EVAV carries a battery pack between 75 and 100 kilowatt-hours. Creating a battery pack like this requires huge amounts of lithium, cobalt, nickel, and manganese. Every additional mile of range requires more of those materials. But if a motor can extract significantly more useful work from every kilowatt-hour stored in the battery, the vehicle can achieve the same range with a much smaller pack. A car that once required 100 kilowatt-hours might only need 70. A vehicle that needed 75 kilowatt-hours might achieve similar performance with closer to 50, which means that there will now be less demand for each of these materials. The entire supply chain begins to shrink. This is what could finally make truly affordable mass-market EVs possible. Not by forcing suppliers to cut prices, not by waiting for next-generation battery technologies that always seem to be a few years away. The future of EVs. Let us start with the obvious answer. Yes, traditional automakers are in a difficult position. Companies that spent the last 5 years committing tens of billions of dollars to lithium-ion battery platforms are now staring at an architecture that could make large battery packs far less necessary. But traditional automakers are not actually the most exposed. The most exposed industry is lithium mining. Lithium producers expanded aggressively throughout the 2000s and early 2020s based on forecasts that assumed battery architecture would remain largely unchanged and demand would scale alongside EV adoption. Now, those projections look far less certain. Markets that currently see electric vehicles as too expensive could suddenly become viable. But if the larger projections prove accurate, the impact goes far beyond cars themselves. In other words, this is not just about making a better electric vehicle. It is about changing the economics of transportation for billions of people. Whether that future arrives quickly or gradually depends on engineering decisions being made right now behind closed doors. But one thing is becoming increasingly clear. If this technology works as well in the real world as it does on paper, It could completely change the future of electric vehicles. The only question now is not whether the industry will change, but how fast that change will happen. In the end, Tesla may have done something far more important than building a better electric car. It may have changed the way the entire automotive industry thinks about efficiency. So after hearing all this, what do you think? Is this truly the breakthrough that will redefine the future of electric vehicles? Or is it just another promise that won't live up to the hype? Let me know your thoughts in the comments below. And if you enjoyed this video, make sure to like, subscribe, and turn on notifications so you don't miss our next story. Thanks for watching, and we'll see you in the next one.